All right, well, hello everyone, and welcome back. In today's video, we're going to continue our coverage of operational amplifiers and learn more about some important real-world applications. All right, here's our goals for today's video. First, we will review some of the topics from our previous video on ideal operational amplifiers. We'll review a little bit of the theory behind those, and we'll also recognize some common real-world applications. We'll also practice solving a couple problems involving one or more operational amplifiers. We will also learn about non-ideal operational amplifiers. And we will learn about how we can apply the offsets model and finite gain approaches to better model these non-ideal op-amp cases. And finally, at the end of the video, we will review a few hints that might be helpful for some of our assignment questions. So let's go ahead and get started. So just a reminder, in the past few videos, we have filled our toolbox with equations and strategies to help us analyze DC circuits. And so amplifiers will be the last topic covered before our first exam covering DC circuits. And in our next videos after this one, we're going to start adding more components to our circuits and make them more interesting. Because in real life, our circuits don't just have resistors and DC sources. In real life, we can also have capacitors, inductors, AC sources, and lots of other things. So in our previous video, we introduced amplifiers. And we say that amplifiers are electric devices that increase the power of our signals. And of course, these are used in many electrical devices and many applications, ranging from communications to computers to sensors. So amplifiers are everywhere. In our previous video, we also introduced the operational amplifier. And remember, when we talk operation, we don't mean like operation in an operating room for surgery. Instead, we're talking operation in terms of performing mathematical operations. And specifically, the operational amplifier behaves like a voltage-controlled voltage source. And so we can use operational amplifiers, or op-amps, to build circuits that perform mathematical operations. And believe it or not, these things have been around quite a while. They were developed in the 50s and 60s, and now op-amps are one of the most widely used electronic elements. And so in our previous video, we introduced one of the most common operational amplifiers, 741 operational amplifier. And we showed how we can actually take this little operational amplifier, plug it into our breadboards, and use it to build amplifier circuits. So you'll remember in our previous video, we introduced this idea of an ideal operational amplifier. We find that operational amplifiers can be quite complex. There's a lot of complicated circuitry inside the little black package, but we treat it as a black box for most of our purposes in this course. What that means is we assume that our ideal operational amplifier behaves much like a voltage-controlled voltage source, and we just worry about the input and output. We don't worry too much about what's actually happening inside the thing. To make things simpler, we assume that the current going into each input terminal must be 0. And similarly, we assume that the voltage at each of the 2 input terminals must be equal. So in real life, it turns out that the current going into each input terminal will not be 0, and the voltage will not be perfectly equal. But most of the time, this is a pretty good approximation. And most of the time in this course, we will assume that our operational amplifiers follow these golden rules. And we saw in our previous video that these golden rules can help us greatly simplify our operational amplifier circuits. So in our previous video, we introduced 6 standard op-amp configurations. If we apply the golden rules and node analysis to different kinds of op-amps, we can derive convenient expressions that show the behavior of these standard op-amps. So for now, we're going to focus on these 6 op-amps that we've covered here. We have inverting and non-inverting op-amps, and you can see that these will multiply our input voltage by some constant. The constant that we multiply by is determined based on the values of the resistors in that amplifier. We also covered the voltage follower, which is used to stabilize signals. And then we also introduced amplifiers that perform addition and subtraction. So where we left off in our previous video is we had started to design circuits that perform math. And we saw that by specifying the values of our resistors, we could design circuits that performed certain mathematical operations. Once again, I do not expect you to memorize all of these circuits, but I do expect you would know where to find this information, so that if I asked you to design a certain kind of circuit, you would know which type of amplifier to use. Let's go ahead and try a quick example. So here we are being asked to design a circuit having one output voltage VO and 2 input voltages V1 and V2. And we want our output voltage to be given by 0.5 times the difference between V2 and V1. So what kind of amplifier circuit would we want to use? Let's take another look at our list. In the case of our example question, we want to perform subtraction. Therefore, we would want to choose the difference amplifier for this particular case. And notice from our equations that we have earlier, we can see, based on our difference amplifier that we know, our output voltage Vout is given by the ratio of R2 over R1 times my voltage difference. So if we go ahead and draw that out, our difference amplifier would look something like this. So we know we want to use a difference amplifier that has the same resistors and layout as shown here. And we know that Vout is going to be given by R2 divided by R1 times V2 minus V1. In this case, we need to select R2 and R1 so that R2 divided by R1 gives us that 0.5 that we need. So you want to make sure you choose resistors that are easy to find so that it would be easy to build this circuit in real life. For example, I could choose my resistor R2 is 10 kiloohms and R1 would be 20 kiloohms. And you would see if I did that, then R2 divided by R1 would give us that 0.5 that we are looking for. All right, so now that we're done reviewing from our previous video, let's now talk a little bit more about non-ideal operational amplifiers. And as we mentioned earlier, a lot of times the ideal operational amplifier is a good approximation for a real operational amplifier. But sometimes, in certain situations, the ideal assumptions don't work as well. And if we look in Chapter 4 of the Circuit Analysis and Design book, we can learn about some alternative models that can be used to model non-ideal operational amplifiers. For the purpose of this course, we primarily focus on ideal operational amplifiers, but the goal here is to show you these other models so that you recognize when you might need to use them. Here's our first non-ideal op-amp model. It's called the offsets model. And so we take a regular old ideal operational amplifier, but notice that we have added some extra parameters. We have added this offset current, and notice now our input currents I1 and I2, they have these other input bias currents running through them. Notice that if we were to set these currents and this offset voltage to 0, we would actually return back to the ideal model. So why would we need to add in these input bias currents and that input offset voltage? Well, sometimes we are measuring extremely small input signals. What happens if our input voltage is extremely small? All of a sudden, if we have background noise and very small voltage in our actual op-amp, we can't ignore the input currents anymore, and we can't ignore any difference between our voltage V1 and V2. So when we're measuring extremely small input signals and we're unable to ignore the small currents and voltages that actually exist in our op-amp, then we can use this offsets model. And this offsets model allows us to account for non-zero input currents and an actual difference between our voltage V1 and V2. So really, the key takeaway to remember for the offsets model is that you want to use this model if you're ever working with very small input signals and you're no longer able to ignore small currents and changes in voltage at the input terminals of your op-amp. Let's now consider the second model, the finite gain model. When would we use this model? The finite gain model actually becomes important when we're working with very large input signals. And so we mentioned before that ideal operational amplifiers behave a lot like voltage-controlled voltage sources. But in real life, we cannot have an infinite gain for a voltage-controlled voltage source. Eventually, a source can only provide so much energy before it maxes out or saturates. And so when we use the finite gain model, we're able to account for the fact that our gain and the signal we're able to produce in our output cannot become infinitely large. So you'll notice we add some resistors in our amplifier model, and we replace our amplifier with a dependent source. But notice, due to these resistors, our source cannot produce infinite voltage and infinite gain. So this model is helpful when we need to account for resistance and a finite gain. So typically this is when we're working with very large input signals and we need to be able to limit the amount of gain that our operational amplifier has. So key takeaway, if you are measuring very large input signals on your operational amplifier, the finite gain model may become useful so that you don't end up with infinitely large gain that is beyond what is physically possible. So you might be wondering now, okay, well, why does all this matter anyway? And so for the next part of today's class, I'd like to cover some applications that you might use or you may have actually experienced in real life. It's easy to look at some of these op amps and just view them as homework problems and things that aren't really that significant. But you'll be able to see from these examples that we cover in this video that these amplifiers really are everywhere. And being able to understand how they work and how they behave is extremely important, even if you don't end up becoming an electrical engineer. So in the next part of the class, we'll go ahead and cover 3 examples of real-world applications of operational amplifier circuits. And we'll apply the tools we've learned in order to solve and design circuits for these applications. One other idea I'd like to leave you with is this idea about how we design circuits in the real world. And in the real world, engineers actually do relatively limited calculations by hand. Especially in electrical engineering, if you are designing computer hardware or circuits, you often use what's called layout software or simulations. And these will allow you to design multi-layered PCBs or printed circuit boards. These are the boards you would find like in a smartphone or in other instrumentation that has complex electronics. So in the real world, the software is going to be doing most of the heavy lifting for you. It will be doing the calculations for you. But at the end of the day, you still need to know the circuit laws and the tools we've covered. Because at the end of the day, you still need to know how these components work and how they behave. The computer alone will not be able to automatically design the exact circuit you need. So it's very important that we understand how amplifiers and DC circuits and Kirchhoff's laws work so that we can actually design and solve problems and develop solutions. So with that in mind, let's go ahead and move on to our 3 applications. We'll talk about electrocardiograms, instrumentation amplifiers, and finally, digital to analog conversion. All right, so our first example involves an electrocardiogram, or EKG. You may have heard about one of these electrocardiograms or seen one of them being done. An electrocardiogram measures the voltage signal from a person's heart. And these are very important in order to diagnose heart conditions. If we see that somebody's heart is producing a different voltage pattern than the normal pattern, that can provide clues to how the heart is working and whether any treatments may be required. And so, how an electrocardiogram works is we put two voltage probes or leads on a person and we measure the voltage across those two leads. And the voltage difference measured is what produces the EKG curve. And there's a very distinctive spike that we see when the heart muscle contracts to pump blood. So it's very important when taking an electrocardiogram that we're able to successfully subtract these two voltage signals in order to produce that curve. This leads us to our first example. There are many applications in engineering where we need to subtract out background noise from our signal. So when we say noise here, this is just unwanted background signal. As you might imagine, the voltages produced by the human heart are relatively small. So the electrocardiogram probes may pick up background noise from other electronics nearby or other signals in the room. So the actual voltage that our electrocardiogram probes will measure will include the actual voltage we want, and it will also include some undesired background noise. And so in this example, we're being asked two questions. Our first question asks us, what type of amplifier circuit should we use in order to subtract the signals? All right, so second part of our question asks, what will be the resulting output if our input voltages are V1 measured and V2 measured as shown? So let's give this a try. So the first part of our question asks, what type of amplifier circuit should be used to subtract the signals? Well, remember, if we want to subtract, that means we need to use the difference amplifier. And notice in this case, we want to subtract. We want to subtract V1 measured minus V2 measured, because that will give us the desired electrocardiogram trace. So basically, we want the out to be equal to some constant. In this case, for the difference amplifier, it will be whatever resistances we choose times V1 measured minus V2 measured. So in this case, the circuit we want is similar to our previous example. We know that this voltage V out will be given by R2 over R1 times V2 minus V1, where V2 is our voltage down at the lower terminal, and V1 is our voltage up top. Notice we want to subtract V1 minus V2. So in this case, we just have to be careful. We want V1 measured to be plugged in for V2, and we want V2 measured to be plugged in for V1. That way we will subtract V1 from V2. So just be careful of your ordering there. And again, Remember to label everything. And so that is the amplifier we would want to use. For the second part of our question, we are asked what will be the resulting output if we are given V1 measured and V2 measured as shown. Well, here's the interesting thing. If we plug in, for our V2, we plug in V1 measured, that will give us V1 of t plus V noise of t. And then if we plug in V1, that's going to give us, in this case, we plug in our value for V2, which is V2 measured. So we have V2 of t minus V noise of t. And here's the interesting thing. Notice what happens to our noise. Our output is going to be equal to R2 over R1 times, notice we get V1 of t minus V2 of t, but the noise terms cancel. So this is a really powerful application of a difference amplifier. We are able to subtract two signals and amplify the result by whatever ratio of resistors we have provided. So not only can we subtract out the noise we don't want, but we can amplify the difference that results. This is a very powerful technique that is often used when we need to measure some signals very precisely. Let's move on to our next application. Another very common amplifier circuit that we see in the real world is the instrumentation amplifier. And so what we do here is we actually take three amplifier circuits and combine them together. Notice first we have two non-inverting amplifiers. And notice what these do. These amplify the initial inputs V1 and V2. So first, we make our input signals bigger so that it's easier to identify them. And then look what we do. Then we send those amplified signals into a difference amplifier. So notice we send the outputs of the non-inverting amplifiers into a difference amplifier. So we're able to amplify each input individually and then subtract the two signals, and this allows us to get a cleaner difference and be able to more accurately measure whatever difference we need between those inputs. Similar to our previous example, this is often used to help suppress background noise that might be present in the input signals. So this leads us to our next example. Let's now consider the instrumentation amplifier shown here. Suppose we define the gain of our instrumentation amplifier as the ratio of the output voltage Vout to the difference between our input voltages. But often, if we want to design one of these instrumentation amplifiers, we want to express our gain in terms of resistance. If we know what our gain is in terms of the resistance values, then we can select resistors that give us the gain we want. So in this question, we are asked to show that the gain of this instrumentation amplifier can also be written in terms of the resistors as the expression shown. Let's take a look and see how we can perform this calculation and find that gain in terms of the resistors. So you'll remember from before, we mentioned that this instrumentation amplifier circuit is actually a combination of other amplifier circuits. So in this case, we know that our inputs are non-inverting amplifiers. And then the output produced by that non-inverting amplifier, well, that's going to be these have some initial intermediate output voltages, and these will be sent in to a difference amplifier. So let's first determine an expression for the voltages that are produced by those non-inverting amplifiers. And you'll remember, a non-inverting amplifier has its behavior given by the relationship V out is equal to 1 plus Rf divided by R1 times V in. And so if you look at the circuits that we are given, we can determine that the V out from the upper input, V1, that is going to be equal to 1 plus, here we have the RF value is actually R2. And notice this resistor R1 is split. Notice we could say that V1 receives R1 over 2, right? We could say that R1 over 2 is associated with the top non-inverting amplifier, and the rest of that resistor R1 is held by our lower inverting amplifier. So we can go ahead and assume that that resistor R1 here is split between the two non-inverting amplifiers. So let's have V1 receive R1 over 2, and V2 receives R1 over 2 as well. So another way to draw this would be to have each of those non-inverting amplifiers having R1 over 2 ohms as their resistor. So if I do that, then my R1 term on the bottom for my voltage V1, that will become R2 divided by R1 over 2, because I'm only receiving half of the resistance from my resistor R1. Similarly, I can say from the lower non-inverting amplifier, I can write a similar expression, and remember my V in will simply become V1 or V2. So now I know that these are my inputs to the difference amplifier. So let's now consider our difference amplifier. And we know for a difference amplifier, we know that our output voltage V out, that is going to be given by the RF value from our feedback loop divided by resistor R, and then we multiply by the difference between, in this case, we have V2 minus V1. And here, notice my inputs are the outputs from the non-inverting amplifiers. So if I substitute that in, I can determine that my V out is given by the following. So notice if I substitute in for my lower output V2, I can just R2 divided by R1 divided by R2, that becomes 2R2 over R1. So I get the expression here. So I can determine my V out is equal to RF divided by R times 1 plus 2R2 over R1 times V2 minus V1. Remember, we said earlier that our gain can be written as our output voltage V out divided by V2 minus V1. So if I rearrange, I can determine my gain, once again, is output voltage over V2 minus V1. So if I move V2 minus V1 to the left-hand side, I determine that my gain A is equal to, in this case, we'll have RF over R times 1 plus 2R2 over R1. So we have successfully derived that expression for gain of our instrumentation amplifier. Let's go ahead and move on to our last example. So another very important application of amplifier circuits is in computers. And we'll cover computers and bits and more on electronics hardware towards the end of this course. But for now, what you should know is that we often store data in computers using binary values or bits. And typically in this case, in the memory, we encode data as a set of zeros and ones, where each bit is a single 0 or 1. And by taking combinations of bits together, we can encode different types of data. Here's an example for a 4-bit piece of memory. So if we have 4 bits where each bit can encode a 0 or a 1, we can actually encode 2 to the 4th or 16 different values. All right, so later in the course, we'll talk a little bit more about how bits and memory work. For now, here's just a very short summary. And what you can do is you can use a sequence of bits to encode certain values. And so here, for example, if I have a 4-bit piece of memory, I can use the voltages V1, V2, V3, and V4 across each bit, and I can have each voltage either be on or off. So I can set each voltage to a 0 or a 1, and depending on the voltages of those 4 bits, I can encode 16 different numbers. For example, if V1, V2, V3, and V4 are all 0, then my resulting number would be 0, because I'd have 0 volts times all these quantities. That would give me 0. But for example, if I wanted to encode the number 5, what I would do is I would set my voltage V1 to 0. I would set voltage V2 to 1, set voltage V3 to 0, set voltage V4 to 1, and I would calculate that my encoded value is 0 times 2 to the third, plus 1 times 2 to the second, plus 0 times 2 to the first, plus 1 times 2 to the 0, and we would get 0, 1, 0, 1 is equal to 0 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 1. That gives us our number 5. So that's just a very brief introduction to how binary numbers and memory could work. You don't need to know that at this point in the course. Again, we'll cover more details on binary and memory at the end of the course, and you'll want to know how that works potentially for our final exam. This is just an introduction, so I don't expect you to know about computers and bits for the purposes of our first exam. Okay, so it's nice that we can encode data into these bits and use it to store memory. And this is actually a very important piece of how computers can perform calculations and do many different types of applications. For this particular application we're going to look at in this video, it helps to know a few more key terms. The application we're going to look at is called digital to analog conversion. And what we mean by that is we're trying to convert a signal from digital format to analog format. An analog signal is a signal that varies continuously with time, and it can take on any value within a minimum and maximum. For example, suppose I had a signal that could range anywhere from 0 volts to 8 volts. Now my analog signal could take on any value within that minimum and maximum range. That's different than a digital signal. A digital signal can only have a set number of values. So what we often see in electronics is that our signal can actually only have a finite number of values. Compare that with an analog signal, where you could take on an extremely large number of values within the range. And in particular, we talked about binary signals in our previous slide, so it's also possible to have signals that can be either a 0 or a 1, just an on or an off. So when we talk about circuits that do digital to analog conversion, what we're trying to do is we're trying to take some sequence of zeros and ones we're trying to take a digital signal and convert to a voltage, which is proportional to the digital value. So this is actually a very important calculation that is done in computers, is taking that sequence of zeros and ones and converting to an actual voltage range proportional to the digital value. This brings us to our last example for today, digital to analog conversion. And here we want to consider this 4-bit digital to analog converter. So in this case, we have 4 sets of zeros and ones with voltages V4, V3, V2, V1. And here we are being asked to determine an expression for the voltage V out for the digital to analog converter below. We are asked what will be the minimum and maximum values of V out for this digital to analog converter. Also told to assume that RF is equal to 4 times R, where R is the resistance used in these resistors. So the first thing you might notice about this circuit is that this circuit contains a summing amplifier. And basically what the summing amplifier is doing is the summing amplifier is summing the voltages from the 4 bits. And then by summing the voltages across each bit, we can convert that 4-bit signal into some analog output or some continuous voltage. So if you'd like, go ahead and pause the video and see if you can correctly determine the expression for this output voltage. Otherwise, let's go ahead and do it together. Well, notice we were conveniently given the equation for our summing amplifier. So what we can do here is we can substitute RF is equal to 4R, and we can substitute the resistance of each resistor. So notice we can find each term of this equation. Let's go ahead and do that. So we know that our output voltage V out is going to be the sum of our first term. Let's go ahead and just proceed in order V1, V2, V3, V4. So our first term has voltage V1, and we are taking V1 is RF over R1 times V1. Then we have plus RF over R2 times V2 plus RF over R3 times V3 plus RF over R4 times V4. So we know that this expression must be true for our amplifier. And now we can substitute RF equals 4R and the values of R1, R2, R3, and R4. If we do that, we determine our output voltage V out is going to be equal to, for our first term, we have RF is 4R in the numerator. V1's resistance is just going to be our resistor R. Then our next voltage, we have, again, our numerator becomes 4R. Denominator, RF divided by R2. Well, R2 is 2R. Then we have 4R over resistor R3 is also 4R. And then finally we have 4R divided by 8R V4. So notice the resistor R cancels on the numerator and denominator. So we are left with V out is going to be equal to negative, we got negative 4v1 plus 2v2 plus v3 plus 0.5 v4. So that is our expression for our voltage V out, given the information we've been provided. Now let's consider the minimum and maximum values of V out. Well, the minimum value, that would occur if our bit has the value 0, 0, 0, 0. When all the switches are in the 0 position, all our voltages are 0. If all of our voltages are 0, then V out will be 0. And then the maximum value, or in this case the maximum magnitude, well, if our bit has a value 1, 1, 1, 1, basically if V1, V2, V3, and V4 are all in the on position with 1, then we determine our V out is going to be negative 4 minus 2 minus 1 minus 0.5. So we determine, in this case, negative 4 minus 2 minus 1, that's negative 7 minus half, it's negative 7.5. So basically our voltage can range from 0 to minus 7.5 volts, depending on the position encoded in those bits. So once again, for the purpose at this point in our course, I don't expect you to memorize the bits and the computer hardware just yet, but I do expect that you recognize how to apply the amplifier equations we've learned in order to solve these problems. Later in the class, we will revisit bits and memory and computers, and we'll get to see more details about how we can use circuits to build computers. All right, so let's go ahead and before we end for today, let's cover a few hints about some common questions that come up at this point in the class. So we often run into some questions about this circuit shown here. I'd like to give everybody a few hints on how you might approach an amplifier circuit like this one. First thing to consider is, what do golden rules tell us about the values of our current and our voltage in this circuit? Well, remember, the golden rules say that if our amplifier is an ideal operational amplifier, which here we'll assume that's the case, we know that our currents I1 and I2 must be 0. Next, we're asked, what is the value of our voltage V2? So V2 is our voltage at our upper input. By the golden rules, we know that V2 must be equal to V1. And in this case, V1 is connected to ground, so V2 and V1 must be 0 by the golden rules. In the next part of the question, we are asked to find an expression for V out in terms of this voltage V and our resistors if we know what voltage V and resistor R is. Well, how would we do that? Let's think about what we know. we just learned about how V1 is 0 volts and V2 is 0 volts. So what we can do is we can do a node equation and do node analysis at my voltage V1. And we can assume some currents. Notice if I perform Kirchhoff's current law, I can say that plus I1 minus I2 minus I3 equals 0. And I can also write that voltage V minus V1 divided by R minus V1 over R minus V1 minus V2 over R equals 0. And wait a minute, what did we say V2 was? V2 is 0 volts. So notice if V and R are known, we can find V1. Well, V1 doesn't tell us what V out is, now did it? But if we know that V1 has some value and V2 is 0 volts, we can then apply Kirchhoff's current law to the node V2. And we would know for our node V2, we could say, for example, if I write in current I4, we could say that we have plus I3 plus I4 minus I2 equals 0. Well, I2 is 0 by the golden rules. So I can say that my current, in this case, I can say I3 plus I4 equals 0. Notice we already know what I3 is from our earlier equation. And then I4 we can write in terms of V out. So we can determine, in this case, V1 minus V2 over R plus V out minus V2 over R equals 0. Remember, V2 was 0 volts. V1 is known from before. We can solve for V out. Last part of the question asks, how could our current I be determined? Well, notice we assume that we have current I4 exiting our node where V out is located. We also have some current I entering, and then we have some current, let's just call it I5 leaving. So to find current I, we can just use Kirchhoff's current law. And we know what V out is. So if we know what V out is, we can find I4 and I5, solve for I1. So please don't be intimidated by these circuits that contain op-amps. Remember, if you apply the golden rules and consider the circuit one piece at a time, one node at a time, these really aren't so bad. Let's cover one more hint before we end for today. Our last hint is about a common question about finding Thevenin equivalent for this more complex bridge circuit. Let's consider a few questions. First thing to notice about this circuit here is that our dependent source depends on current I1, But there is no other source present to produce current I1. And the circuit is also connected at the moment to an open. So if there are no other sources present to produce a current I1, then in this case, our current I1 must be 0 because there is no other voltage source that does not depend on I1 that can create a current. So you should see in this case that I1 must be 0. At least when the circuit is open. That's because there is no other source that is producing a current, therefore the dependent source is unable to produce a voltage. Next part of the question, how would you determine Thevenin voltage? Well, remember, Thevenin voltage is just the same as our open circuit voltage. And so if we know our current I1, remember we know that there is 0 current coming in, I1 is 0, so here we can determine what our voltage across resistor R2 will be. And similarly, we can determine, again, if there's some current flowing in this lower portion of our circuit, we can determine, all right, what might the voltage be across resistor R4? And so if we can determine the voltage when walking across from one end of our circuit to the other, we can determine what that open circuit voltage will be. Another approach you could use to find Thevenin voltage is to consider voltage division. If we know I1, we can find the value of this voltage source, and we can consider the upper and lower loops separately. So voltage division or Kirchhoff's voltage law could work fairly well here. The last part of the question asks about determining our Thevenin resistance. So remember, when you determine Thevenin resistance, for our purposes, we like to connect that external source VEX that supplies current IEX and solve for VEX over IEX equals our Thevenin resistance. So at first, this calculation might appear a little bit intimidating. But let's remember that procedure we covered in our earlier videos about how to approach these more challenging circuits. If you apply the approach that we've demonstrated in our previous videos, you might recognize that this is a supernode. And if you see a supernode, you should be happy because this gives us free information. If I assume I have voltage V1 to the left of my supernode and V2 to the right of my supernode, I can get an expression. Notice I can say that my voltage V1 plus 2I1 must be equal to V2. And in this case, since I have an external source VEX connected, I cannot assume that I1 is 0 anymore, because there is some current IEX being sent into my circuit, so I have to consider my current I1 for my Thevenin resistance calculation. If I rearrange, I can determine that my current I1 can be given by V2 minus V1 divided by 2. Notice what else we can do. I know that my voltage at the top of my circuit will be equal to VEX because of my source being attached. So I can also write the expression that my current I1 is equal to VEX minus V1 divided by R1. So I can use these equations to relate my external voltage source VEX to the supernode voltages and to my current I1. What else can we do at the supernode? We can also apply Kirchhoff's current law at the supernode. And so a really good approach for this circuit is to recognize that we can apply Kirchhoff's current law at the supernode, and we know by Kirchhoff's current law that plus IEX minus I1 must equal the current I2 flowing through the other branch of the circuit. So if I use Kirchhoff's current law at both of these points, I can determine an expression for VEX divided by IEX, and that will give me my Thevenin resistance. So make sure you keep all the tools in our toolbox handy, and remember that procedure we covered to help simplify these more complex circuits. And if you have any other questions as you're working on these problems, feel free to reach out. So let's go ahead and wrap up today's video. So hopefully now you are more comfortable using ideal operational amplifiers and our known amplifier circuits to solve circuit problems. So make sure you're comfortable using ideal operational amplifiers and designing circuits containing one or more of the operational amplifiers we've covered. Also, make sure you recognize when we would want to use the offsets model and finite gain in order to model non-ideal amplifiers. And be sure to keep those hints we covered in mind as you work on our next assignment. Thanks everyone for joining the fun, and we will see you in our next video.